Okay, if you remember from Monday, I talked about unsaturated and saturated. Saturated means alkanes. Remember the hydrocarbon family. Unsaturated means it's got double or triple bonds in it. So alkenes are unsaturated. Now, there's alkenes and alkynes. Alkynes are triple bond, and there are no triple bonds in your body naturally. Okay, and this class is allied health. So we're not going to study stuff that's not naturally in your body. That same goes for plastic polymers. We're not going to touch those either. Okay, there's something else called aromatics. In cooking, they always talk about add the aromatics. What do they mean by that? Who likes to cook? Okay, we run across that before?
Garlics, onions.
Yeah. Yeah, stuff that's got some bite to it. In chemistry, aromatics are not that. Aromatics involve a chemical called benzene, and I'll talk about it today. Okay. Now, if you remember from Monday when we were naming the chemicals, we put them in alphabetical order, like on the branch naming. You have to ignore the number of them. In other words, di, tri, tetra, that doesn't come into the alphabetizing. Only the main part, like ethyl, propyl, methyl. One exception is iso, like isopropyl or isobutyl. The I is not ignored in that one. Okay, let's talk about naming now. All right, so the functional group in an alkene is the double bond. The thing with the double bond, there are two carbons it attaches to. And you're only going to name one of them. Now, remember we talked about naming it two different ways? Let's look at this one here. This guy here. All right. Notice if we name it, if we start numbering from the left, the numbering from the right favors a lower number for the double bond. Okay, so which means we're going to start on the right and go to the left. So the first carbon of the double bond we run into is on carbon number 2. So that's the one we're going to specify in the name is the one we run into first. And that's why it depends a lot on how you number it. Because if you number it the other way, it's going to end up being the other carbon. So always want the lower number. Okay, so the backbone here is very straightforward. Do we have any branches? There's a seat over here. And there's some seats in the back as well, depending on your preference. All right. And by the way, if you have any trouble with me, you're not being able to hear me, just raise your hand and go like this with your ear. And I'll know I'm not speaking loudly enough, okay? All right, so no branches. No carbons off the backbone. Okay, so now we get into it. So that means there's only going to be 2 parts to the naming. How long is the backbone? 6 carbons long. So it's going to be a now, instead of ane, it's going to be ene, E-N-E. Hexene. And what carbon does the hexene start on? 2. okay?
Why does it start on two?
Because that's the first carbon, when you start at carbon number one, you run into where the double bond starts.
Oh,
Couple more examples here, okay? It's an alkene, double bond is closer to the left than the right, so we're gonna start numbering on the left. And we can either go straight across or go up. Let's go up. So that's the backbone. We have one carbon off the backbone, so that's gonna be a branch. And it's on carbon number 3. Four carbons long, so it's gonna be a buta. And it's the butene. Starts on carbon number 1. So this is back, let's do this differently here. I pushed the button on my stylus. The 3 parts. Okay, so again, this is the functional group. Backbone. And branching. Now you can have multiple double bonds also. Yeah,
For the three methyl thing, is it for 1, 2, 3 over on the branch, or is it going backwards from 4 through 2 to the double bond?
branching occurs on carbon number 3. That's what the 3 stands for.
Okay.
Is that your question? Where did the 3 come from?
Yeah, so does that start on the first branch or, yeah? Kind of, weird.
Yeah, because in this one, we have the option of doing 2 different backbones. They're totally equivalent though. Going straight across or doing an L.
Yeah.
I just chose the L just to be honoring.
Okay.
Okay, let's do the next one down here. And the dry labs give you lots of practice on naming. Now, regarding the dry labs, for Wednesday, folks, you're gonna need to get a good start on the first part of the dry lab, which is on Lewis dot structures. We're also gonna be choosing a partner, a lab partner, also gonna be choosing a drawer. You're gonna be taking inventory of the drawer, and you're also gonna be making sure you can work combination one. Those are the things we're gonna be doing today. Okay, everyone got out around, who's the last one up? Did we get out around 4, something like that?
4, 3, 5.
That's when it ends, but we didn't go this far. You were there towards the end. When did you leave?
4 o'clock-ish.
Yeah, I was thinking too. So, and it's kind of hectic in the beginning because everyone's choosing drawers. You got to take a picture of the back of your lock. And so I can give you your combination. It's hectic. Normally they're not like that. They're much smoother. It's just day one. Okay, so let's look at this one here.
Quick question. Is this different from naming the alkanes?
No,
No?
no. It's just that alkanes sort of don't have a functional group.
Oh,
Where from now on, everything is gonna have a functional group.
okay. Then for the attached groups, I thought like the backbone was considered if it was attached to like the ending, like as an extension. as opposed to like being in the middle of the.
The backbone, okay, the question was about the backbone. By definition, the backbone has to include the functional group. Now, with alkanes, you really don't have a functional, group, so just kind of belongs one. But from now on, the backbone has to, no exception, has to include functional group. So this functional group is a double bond, so your backbone has to include the double bond.
I think I'm getting confused, but, like, the CH, like what is numbered as number 4?
Top one,
Yeah, I thought that's not considered like part of the backbone. Like, how is it considered part of the backbone if,
my yellow marker went through it.
I'm still not understanding.
This particular one, you can have two different backbones. But has the same number of carbons in it though. So it's gotta be, if you have two round, let me show you the other one. This is the other one. Straight across. And see it, and notice it includes the double bond. They're both 4 carbons long. So if it's an equal number of carbons, you get a choice. Which one do you like better? Doesn't matter. Because see, the branching with the orange one now occurs at carbon number 3. With the yellow one, the branching occurs at carbon number 3. So there's no difference. And the name is going to be the same. As long as you choose the backbone, the longest backbone that contains a functional group. On your dry lab. Part 2 of your dry lab is on alkanes. And then the next set of worksheets is on alkenes and alcohols. And a lot of it is naming. There's a fair number of reactions, but the naming part, you can go through there and practice that. I also have the answers. I want to make sure you're doing them right. Also, that's why I'm there in the dry labs as well. Are you Wednesday?
Yes.
Okay. All right. Let's go on here. Okay, so we've got this guy down here. And okay, here's the functional group here, the double bonded C. So our backbone has to include that. And we are going to go with yellow now. Now, if I went straight across, there would be 5 carbons. But if I go down and around, it's 6. We want the longest backbone. Okay, so that's going to be a hex. A hexene. And we have a branch on carbon number 4. Okay, the double bond starts on carbon number 2. We have to identify where it is. So when we do alcohol, the alcohol is defined with an OH. We have to say where the OH is located. Now, sometimes we can have a combination of a double bond and an OH. So the naming gets just a little more involved. Okay, so does this make sense? Okay, you can have cyclic double bonds. You can have multiple double bonds. Let's look at the multiple one first. Okay, first thing, backbone. Okay, it has 2 double bonds, so it's got to include both of them. That's our only option that includes both of them. So we've got 2 branches, 2 methyl branches. So that's going to be a dimethyl. Oh, numbering. Let's look up numbering for a second. Okay, this one numbers from right to left. Let's go left to right. Notice it doesn't change. The branching is the same, so it doesn't matter which numbering system you use on this particular one. We have branching at carbons 2 and 3, either way. And we have the double bond, first double bond starting on carbon 1, either way. So it doesn't matter which one you choose, you'll get the same name. Okay, so this was going to be, notice, we have to indicate there are 2 double bonds. And it's at positions 1 and 3. So those have to go together. If there were 3 double bonds, you'd have a triene. Now, biochemical molecules frequently have double bonds. Frequently, like probably 95% of the time, if not more. So you can have tetraene, pentaene. When we get into fatty acids, the omega-3 fatty acids, some of them have 6 double bonds. So you have hexene, pentene. So anyway, bottom line is double bonds are very frequent in biochemicals. Okay, so we've got 2 branches. And again, the di, whenever you have di, you have to have 2 numbers that represent each one. Okay, does that make sense? All right, let's look at the cyclic version here now. Okay, anytime you have a cyclic compound, that automatically is the backbone. Boom. So it's okay. So now the cyclic ones are kind of tricky. Let's do a simpler version first. Let's name this one first. Okay, so automatically the cyclic part is backbone. So we can start numbering from here. Or we can start numbering from here. We can also number clockwise, and then you go the other way, counterclockwise. Okay, so counterclockwise is the blue, clockwise is the red. So which one should we use? Well, we've got a methyl branch here, carbon number 1 or 2. So let's name it like each one is valid. So let's name the blue numbers first. So this is going to be 1 methyl, because it's on blue carbon number 1, and it's our double bond starts on carbon number 1. Okay, so that's one of them, using the blue numbers. Let's switch over to the red numbers now and look at the difference between the two. Bless you. Okay, using the red numbers now, the methyl branch is on carbon number 2. Double bond is still carbon number 1. Okay. So, bottom line, which has the lowest number, blue or red? Blue. So that's the correct one. Now on the test, if you were to put the red one down, I would give you partial credit. Because you understood the concept, you just didn't figure out the numbering scheme. I'd probably take off, it's worth 6 points typically, I'd probably take off 1. Now, this one, the only difference between this one and the one we just did is it has 2 double bonds. You just have to notate the diene as it relates to where the double bonds are. And again, you have to count, do 2 countings, clockwise and counterclockwise. Always do multiple counting, particularly in the beginning. This set of slides does not do that. Okay, so are there any questions about naming? Every test has 3 parts: intermolecular forces, naming, and reactions. Okay, so let's continue on here. Now, we're not going to get into bond hybridization. It's out of the scope of this class. Now, having X'd out those 4 slides, I want to emphasize something. Rigidity. Double bonds don't freely rotate. Single carbon bonds do rotate, unless they're cyclic. Okay, with alkenes, it doesn't matter if they're cyclic or not, they're rigid. They won't, there's no movement at all. And we're also going to have cis trans. Between the two, what do you think is more stable, trans or cis? Yeah.
Is it cis?
You go with cis, what do you go with?
I also want cis. Cis.
Both cis, right?
Okay.
And we have a trans. Okay. Remember we talked about Monday steric hindrance? Between the two, which has most steric hindrance? Cis or the trans? Did you say cis? Because they're closer together. The universe doesn't like that. Trans makes them farther apart. So trans is more stable. Now, the big deal on that is our diet. Whenever we mess with a fatty acid, in any way, what happens is the double bonds will revert to trans. Our cellular membranes want cis. So by messing with those double bonds, it's going to revert to the more stable version, which is the trans. Okay, so cis has more hindrance, trans is more stable. Now, the physical properties are similar, but not the same. It has to do with how good of a fit between the two molecules. Trans fit better when you go trans to trans. Cis to cis are lopsided and they don't fit together as well. So that's why the physical properties are different. Boiling point. Also surface tension. And surface tension aren't the same. Physical properties basically are the same as alkanes. Doesn't conduct electricity, it's flammable, very nonpolar, very similar. And like alkanes, the bigger the alkene, higher the boiling point, higher the melting point, more surface tension. All right, reactions. Reactions are the death knell for 306 students. They go, oh, this is a great class, except for reaction. Reactions are where the meat of this class is. Okay, so we're going to talk about a little bit of everything. And I want to stop a minute. And I want to put okay. I want to walk you through this flow chart. Now, flow chart is incredibly useful. This is one last thing you have to memorize in this class are the reaction types. You've got to figure out structures of the reaction and the conditions. You don't have to memorize all of this. I'm going to give you this on the test, right? You always have this out when you're doing reactions. Okay, normally people talk about reactants, products for a reaction. Reactants is what you start with, products is what you end with. Products are normally more stable than what you start with. And that's why the reaction occurs. Sometimes that's not true. There's another factor in there that can push the reaction even though it's not more stable. It's called entropy. Most of the time, though, that doesn't come into play. Okay, so notice there's an arrow there. All these down here have arrows as well. The head of the arrow are the products. See where the head of the arrow corresponds to the product. The tail of the arrow corresponds to the reactant. So, starting with an alkene here, right in the middle here. Okay, in certain situations, the alkene is the tail of the arrow. Sometimes it's the head of the arrow. Sometimes it's a reactant, sometimes it's the product. Okay, so let's figure out what we're trying to do here. Okay, I'm going to talk in a minute about addition reactions, which is this one over here, and this one over here, and this one down here. Okay, so notice that all three of those, talking about this guy, and this guy. The alkene is at the tail. It's on the reactant side. The head of the arrow points to the product. So in this case, we're going to make an haloalkane over here, and it's different than this haloalkane. And then down here, we're going to make an alcohol from an alkene. Now, alkenes, like I was saying at the beginning, aren't very stable. So they want to react. Excuse me, they want to react, form something more stable. Head of the arrow is always more stable, tail of the arrow. Products are always more stable than the reactants. So, to make this kind of a haloalkane, I'll show you what that means. We're going to do one thing. We're going to add bromine or chlorine gas. And that's going to add across the double bond. If we want a different kind of haloalkane, we're going to add hydrochloric acid over the double bond. Notice one other thing. I told you to expect a mix whenever we're adding the HCl or HBr. Okay, so let's go into detail for these two reactions. So one of the reactions going to the left was we're looking at Cl2 and the ones going to the right, we're looking at HCl. Now, the reason why they call it an addition reaction is because we're adding across the double bond. Statistically, it's 50-50 which way you're going to add. Let's do the bottom one first. We add the HCl to this. The A corresponds to the H. Cl corresponds to the V. It's going to be added like that, half the time. The other half the time is going to be flipped. Like that. That's why there's a mixture. Now, when we're adding something homogeneous like Cl2, the Cls are equivalent. So the same thing happens, is just you can't tell them apart. So in that situation, it's going to be like that. So it depends on what we're adding across that double bond. Now there's three versions of that. We had something like Cl2, HCl, and the last one is going to be water. You can also add hydrogen gas across it as well. But this is the one that's going to be a mix. This is going to be a mix. And this is no mix. No mix. All right, the simplest one is going to be adding like bromine gas or chlorine gas. And what's going to happen is the Br is going to add to either side of the double bond. See, does it have an example? No. So let's look at an example. So we're going to take this 1, 2, 3, 4, 1 butene. And we're going to add chlorine gas. So the chlorine, remember, is like this. So the one chlorine is going to go one side, other is going to go to the other side. So we're going to end up with so this is going to be 1, 2 dichlorobutane. This is called synthesis. This is what drug manufacturers do, ag manufacturers do every single day, 24/7. They synthesize stuff. You start with reactants, you have conditions, products, 3 parts. You have to name the 3 parts. Name the reactants. In this case, it was 1 butene. Condition, Cl2. Product, name them, 1, 2 dichlorobutane. Which is more stable? The butane or the butene? Butane. Products are always more stable unless we have entropy involved. Then that doesn't necessarily hold true. Like a cold pack, for example. The reaction goes, but it gets cold. That means the product is not more stable than what we're starting with. So entropy forces that reaction to this, okay? What about entropy? I'm not going to talk about it anymore. That's part of Gibbs free energy from 305. Okay. So that's your first reaction. First one. And the reason why alkenes are more unstable than alkanes is because that double bond has 2 kinds of electrons. And one of them is more unstable than the other one. One's called sigma, don't write this down. The other's called pi. The pi electrons, what makes that double bond unstable. You have a triple bond, you have even more pi electrons, even more unstable. That's why acetylene gas is so powerful. Triple bond. Okay, so does this process make sense? So you're going to have reactions on your test. You need to include all 3 parts to get full credit. You have to predict product, you have to know the conditions which come off of the flow chart, by the way. And you need to be able to name reactant and product.
So what are the 3 parts again? Just so I have, like, what-
Name the reactants, products, conditions. And then predict the structure you're going to get as well. And each one of those I can give you partial credit for if you don't get them all there. That's why I don't do multiple choice. Now we can also add H2, hydrogen gas, across the double bond. However, it doesn't work very well. So what we have to do is we have to put a catalyst in there, which is platinum. But it can be other kinds of metals. They frequently use platinum because it doesn't go away. It's real expensive to buy, but you have it forever. So that process is called hydrogenation. One of the companies, Cisco, no, not Cisco, Crisco. Who knows what Crisco is? Yeah, what is it?
it's like short answer.
It's a short name. It's a substitute for fat or lard. I grew up, my mother cooked a lot. Everything's from scratch with her. And she used Crisco because she thought it was healthier than lard. The problem with Crisco is they hydrogenate fatty acid in oil to make it more lard-like. remember I said whenever we mess with fatty acids, sometimes we'll get the trans conversion, it's more stable. So the old Crisco was loaded with trans fat, horrible. When I grew up, my mom used to make pies once a week. Once a week, hot pies, apple, whatever. And guess what was always on the counter? Crisco. Now Crisco almost went out of business because of this problem of trans fats. So what they did is they came up with another method to convert oil, seed oil, to a fat-like product with no trans fat. They just mix rather than apply heat. But Crisco almost went out of business because of this. Okay. Now, sometimes when we get a mix, we don't know which one is more stable. And there's two properties of molecules that you need to consider determining which is more stable. One is called Markovnikov's rule. And this has to do with terminal hydrogens. So if we've got this guy, and we have so say this is our product. You have to circle which one is more stable. So whenever you have a mix, which is more stable? Count the terminal hydrogens. How many hydrogens are in this end? Up here. Remember now, carbon has 4 bonds. One of them is carbon to carbon. All the rest are carbon hydrogen. So that's 3 hydrogens. On the other end are 2 hydrogens. Because 2 of the bonds are part of the double bond. Okay, in this one here, we have 3 hydrogens and 3 hydrogens. Which one has more terminal hydrogens? Bottom or top? Bottom. More stable. Now, there's another reason it's more stable. So this is going to be, we're going to call this Markovnikov, or Mark for short. And this is going to be symmetry. Between the two molecules, which is more symmetrical, bottom or top?
Bottom.
Bottom, which is more balanced? Bottom. Nature does not like unsymmetrical molecules. It loves symmetry because they're more stable. So, symmetrical reasons, so I go mark, check, sim, check. So those 2 reasons, the bottom one is more stable. Symmetry and more terminal hydrogens. But whenever you get a mix means more than one product. Okay, let's look at this example down here. Okay, so we're starting with, this is propene now, 1 propene. I'm going to add to that double bond HBr. Now, H and Br are not homogeneric. They're heterogeneric. Whenever you have a hetero addition, that's when you get a mix. So it depends on which way the H and Br land. 50-50. That's why we end up with this guy here and this guy here. So let's analyze why the red box is around the second one. Okay, so we've got. So this is gonna be 1 bromo propane, 2 bromo propane. All right, symmetry, which is more symmetrical, right or left? Right, it's more balanced. Okay, so symmetry wins here. What about Markovnikov, terminal hydrogens? How many do we have over here? How many on the other side? How many? 2. Okay, here we've got 3 and 3. So Markovnikov has more terminal hydrogen, so it's also more stable. Now, if we think of water, I'm going to go through one more reaction today. We're going to add water across the double bond. So when we think of water, I want you to think of as H bond OH. Okay, H bond OH, like this here. Okay, so what's going to happen is one of the 50% random hits is going to have the OH on the right. The other 50%, which is going to be on the left. Hence, you're going to have a mixture. And we have to go through the same thing with the mixture, which is more symmetrical. We look at Markovnikov's terminal hydrogens, which is more symmetrical. Notice it requires an acid. Now, sometimes the acid is just H plus, or they'll say H2SO4, sulfuric acid. It depends where you're getting the reaction from. They're equivalent though. Doesn't matter which one you use. Okay, so we're starting with this, which is a 1, 2, 3, 4, 5, 6, 7. So it's a heptene on carbon number 3. And we're going to end up with same backbone now. Okay, and one time it'll be there. Again, it just depends how the water lands. Now, we haven't got to alcohols yet, so I'm not going to name these. It's fairly straightforward to name, but I'm not going to name them now. I'm going to wait till we do alcohols. Okay. Which is more stable? Well, if we do Markovnikov, they're the same. 3 H's, 3 H's, 3 H's. So using Markovnikov analysis, we can't determine from that which is more stable. Symmetry. What about symmetry?
One on the right.
One on the right. The OH is more centered. Hence it's more stable. So by using those together, you can usually figure out which is more symmetric. Sometimes it's really hard. The more complex the molecule, the harder it is. And if it's on a test, if it's a complex molecule and you get it wrong, I'm not going to ding you for it. If it's a simple one though, yes, you need to make sure you understand the concept of symmetry. Okay, so we have 3 minutes left. So I'm going to go back up to so we've gone over 4 reactions today involving alkenes. We can add a homogeneic addition like H2, Cl2, Br2, no mix. If we add a heterogeneic mix, then you end up with a mixture because you're going to get one time this way, another time the other way. And then you need to determine stability, which is more stable. So now you need to practice these. You've never seen these before. Never before at this detail. Now, and if you're taking 420 instead of 306, there's another layer of detail you go into there called mechanisms. And that's where you actually show why this reaction happens. And you have a little something called a nucleophile and electrophile, and that's why they attract, and this is why they attract. It's called a mechanism. I chose not to do any mechanisms in this class. The main thing I want to focus on is reactions, naming, and intermolecular forces. Okay, that is it for today. We covered a lot of material today. And our technology works. Okay, so any last minute questions? Now I'm going to clean up here and I'm going to go to lab. So if you want to start lab early, all right, if I'm in here at 3:15, you can come right in. You don't have to wait till 1:30. Don't go. Think about lab partner, computer group, lab partner, and the drawers are marked 306 and 400. You can choose an even number 306. Which is it don't make sense when you see the drawer.
Yeah.